think that's a good thing to say. I think it's a good exactly. Okay, so I'm looking forward to seeing where he's posted this. Half of these things are on size.
All right, good morning. How's everyone doing?
Good, how are you?
It's hard to complain on a day like this. It's supposed to be like 72 degrees. I hope you don't have to be inside this afternoon. We have a big one today. We're going to wrap up GLM, and then we're going to talk about our one of the first applications of GLM, which is the binary outcome model. So that's what we're doing in class. Y'all living your best lives?
Trying to. Yesterday was really nice.
Yeah.
It was fun.
Yep.
I went outside.
Okay. That's nice.
Yeah.
Do you have time to go outside today?
Hopefully, yeah.
My mood just like radically changes when Pittsburgh spring hits. Like when the grass gets mowed, that smell just gets me for some reason. And have you running the marathon?
I think Riley might be.
Okay, nice.
She's a part of the triathlon team at least, so I think she might be training for it.
Okay, that's exciting. Yeah, early May, first weekend of May. If you're in Pittsburgh, it's really fun to watch it too. Like you don't have to run to get excited about it. Okay. So let's see. Tomorrow we have our third checkpoint. So you can drop in, or you can email me for the copy. It's going to be behind a code again, so you can't just access it. You have to do a little bit of work to get access to the checkpoint. But I recommend you be in person. Usually the way that goes, at least there are a couple of people with questions, and people are talking to each other and such. I mean, I think at this point you know how it goes. And then at the end of the semester in the course evaluations, so you can be honest, you can say whether you liked it or not. You can tell me directly, you don't have to do it anonymously, but it's a bit of an experiment. I'm curious how it's going for you. So we have GLM to finish. I think there were enough questions about it after class and in my office that I wanted to double back and just talk about a few things before we press forward. So that's what we're gonna do at the beginning. And then we'll talk about binary models. So if you're familiar with like Probit and Logit, those models are simply extensions of GLM. So we're going to talk about them first in the GLM context, but then also in their own framework. So that's where we're going. In the scope of the class, I just want to talk about where we are and then just frame the context. I think sometimes, like, especially when we're talking about these kinds of models, like maximum likelihood and GLM, it's easy to forget sort of like we're getting into the weeds on a lot of this stuff, and it's easy to forget the high level concepts, which to me as a learner, I think for me personally, it's important to think about the high level concepts, like why are we doing what we're doing, as we get into the weeds. The weeds are incredibly important, like that's where the true like nitty gritty of the work happens. But I think also the high level ideas are also where the work happens. And that's what allows us to sort of motivate the kinds of things we're doing. So conveniently, I've put this website together, which allows us to hold all the high level ideas all in the same place. What we're doing with this class is really talking about estimation methods that are sort of more general than what we do with regression. Sometimes the the thing you're trying to model doesn't work very well with regression. And so in those contexts where you turn to these ideas. So we started off with numerical estimation, which was really just like numerical derivatives. So this was, what if we don't take the limit as the epsilon goes to infinity or goes to 0? And what this gave us was, first off, a lack of precision. Like we're not thinking in the world of perfection like we do in mathematics. We think of estimation or approximation. But the other thing it gave us was the ability to not need to write down functional forms, which for a lot of models, writing down a functional form is either too difficult to do or impossible. Like sometimes it literally is just impossible to write it down. We also talked about simulation. So what if we know the data generating process, either because we're trying to estimate something mathematically and we know the math, we just don't know the solution, or we have some like model assumptions that we bake in, which will be important for us later today. And then we started talking about nonlinear least squares, which was the first real context where we started taking off the OLS assumptions. We said, what if we could have a function that was not linear? So f of x equaling y, our model specification. What if that function was not linear? So that was the nonlinear least squares. We also did quantile regression, which is the other kind of like relaxation of OLS, which was instead of thinking about minimizing mean squared error, what if instead we minimized something else? So the first thing we did was like absolute error. So like we took the absolute value of the errors on either side. And what that gave us was this more general context for thinking about estimating models. That was our first sort of foray into these more sophisticated models that we're in the process of developing. Maximum likelihood, I think, is, it's so general and so powerful. Really, the rest of what we're doing this semester is built on that foundation. We said, what if we, instead of not requiring there to be a specific data generating process, what if instead we baked in a distributional assumption? So we said, what if I know the distribution I'm drawing from? What that gives me is the ability to model the data generating process directly. And what that also gave us was the ability to write down a likelihood function. And that's, as soon as we have a likelihood function, then we can just try to maximize it, which is the entire idea of maximum likelihood. So we just try to find essentially the peak of this like product of probability distributions. So that was a pretty big idea. And then we said, look, GLM actually can do all of it, or almost all of this for us. Not all of it, but almost all of it, with some very general kinds of models. So that's where we are. And I think last class we covered it. Maybe it was either too fast or in not enough detail. But I want to go back and just secure some of the core ideas before we move on to binary outcomes. Before we do that, are there any questions? These are the kinds of models, like, I think 90 to 95% of the time we run ordinary least squares. These are the models that, allow you to be sort of good at more than just the basics. And it doesn't actually take that much extra work, which I hope I'm convincing you of. So I just want to walk through some extra stuff I added to the notebook. This is maybe a little bit out of order, but I just want to go back and make sure we're on the same page about a few things. So the basic ideas you'll remember are that we have sort of this unified framework to think about maximum likelihood. So we have this probability of probability families. So these are sort of the shape of the distribution, and they all sort of they have a common characteristic, or a set of common characteristics mathematically that sort of allows us to work with them as families. And then within each one of those, we have a linear predictor for the model parameters we're interested in. So there's this sort of characteristic parameter, usually that's the mean. And what we're doing is trying to estimate that characteristic parameter using a linear predictor, which is this thing. So this is our eta. And then we have a link function that takes eta and maps it into the parameter. So we're not going to directly estimate the parameter, but we're going to estimate the predictor, the linear predictor, and then link it to the model parameter, which in general is going to be the mean. So if you have all of this, you can then just run this thing, smf.glm, which is going to just directly implement the general linear model. And what I'm going to show you today, I added this to the notebook since we last talked. We're going to estimate the GLM with the normal family using the identity link function. And I'm going to show you that that's equivalent to OLS. So what we're doing with GLM is a larger class of models that sits between maximum likelihood and OLS. So it sort of captures OLS and is a strict subset of maximum likelihood. Okay, so these are just the prereqs. I have some nice school pride colors. So this is really just review. This is the family of distributions. We call them the exponential family. They have a particular mathematical sort of symmetry to them. So Gaussian or the normal. It's funny. I'm in a sort of a part of the world on the internet that involves like video editing. So every once in a while I hear people in the video editing world talk about like a Gaussian blur, which is like a way of doing like blurring. But they all pronounce this wrong. They call this Gaussian. It's Gauss. And then these are just some of the others. We're going to talk about multinomials after binary. We're going to be two classes after binary. So this is the basic model for the predictor. So we have a linear predictor that we're embedding. It looks like this. So this looks a lot like OLS, except we're not directly estimating a conditional mean using eta. What we're going to do is use a link function to link eta to our model parameter, which is sometimes mu, but we're going to, we'll use different notation depending on the context. But the main idea is that we're linking the linear predictor to the model parameter, whatever that is, mu, using G. And we require G to be invertible, at least theoretically. Some of these will not be like, one of them we'll talk about later is the CDF of the normal distribution. Sometimes we use that as a link function in probit. That is the link function in probit. And it's invertible, but it doesn't have a closed form inversion. So it doesn't necessarily need to be nice mathematically, but it needs to at least be invertible. Okay, so nice. So this is the model we run. we're trying to estimate mu using the inverse of g, which is, it's taking in the estimate for eta, which we're assuming to be just a linear function of betas and x. Okay, so this is all review. I think there's maybe some, I wanted to include this just to write this out, to make this exceptionally clear. In OLS, this is what we're doing. And in nonlinear least squares, we say there's a model, which is the linear combination of predictors times the betas. And then in addition to the model, we're trying to get the model as close as we can to the data. We will never be exactly at the data. So there must be this error term. And then we do make a distributional assumption in OLS, but it's on the error term. So we're saying that the error term needs to be normally distributed. In practice, we can relax this assumption, like we've talked about. Like, you can relax that assumption if your sample size is large enough. By the central limit theorem, this normality assumption becomes less important. Because what we generally care about is the distribution of betas when we resample. But this is the mathematical assumption we bake into OLS. In GLM, the randomness we write it down differently. The way we conceptualize what we're doing with GLM is just slightly different. Instead of having epsilon as sort of the mistake of the model, what we think about what we're doing is trying to model lambda. We're trying to say, how do we pick lambda? Which in the Poisson model is both the mean and the variance. But it doesn't need to be both. Just some parameter that governs the shape of the distribution we're drawing from. But then the way we model the randomness is not with an epsilon. It's with y being the draw from some random variable. So we're assuming y is being drawn from a Poisson distribution, and then we're saying, how do we know which Poisson distribution it is? And then we maximize the likelihood over lambda. So there's no epsilon. So this is sort of a structural difference between the two kinds of models. But I'm going to show you that they give us the same results in a second. Okay, any questions about this? I had some nice conversations in my office about these kinds of things. I have a little spinner on my door that tells you whether I'm in or out. You all can just knock on my door if I'm in and just say hello. If I'm busy, I will tell you to go away. And then if I'm not so busy, I'll tell you that too. I might say, like, I don't really have a lot of time, but if it's quick, we can chat. But feel free to knock on my door when it says green. I love that. Okay, so in part 5, in topic 5, we covered the Poisson using goal scoring. So this was, we talked about the average level. We talked about the home field advantage, the scoring ability, and then the defense score. And what we saw was this was, it's linear. This thing being eta is linear in model parameters. We're just estimating the abilities for each of the teams. And this was the log link. So what I've done here is just invert the log. So we just raise both sides to the exponent, the exponential, which gives us this thing. So this is like lambda is equal to g inverse of our model. So the betas times the x's. So we've already seen this before. It looks like this. So what's nice about this is it allows us to model more complicated situations, But the downside, like we talked about last time, is that this is just much more challenging to interpret. When we talk about the binary outcome model, I'm going to show you one way of communicating the equivalent of marginal effects for these GLMs. So there are some nicer ways of communicating the effect of any one of these parameters. But this is one of the core challenges with these nonlinear models. The linearity of regression makes our job of communicating our results just much simpler because we're just communicating averages. But there's a way of sort of translating the idea of an average into the nonlinear context. So we'll talk about that later. So this is just some of the things we said last time. It's more challenging to interpret the parameters. So these are some common link functions. The identity function, this is the one we use in OLS. So we're just saying there is no like function that we're transforming. It's just a linear relationship. And the way we would express this in OLS is just something like this. So it's like mu is just equal to our betas times x. We're not going to write the epsilon, but then we say then y is distributed normally, centered on mu. And then with the normal distribution, we also need sigma, or sigma squared. So this is OLS, but expressed in GLM terms, where we don't have the epsilon. We're just saying we want to pick the mu that maximizes the likelihood given our data. So a bunch of observations I coming from some underlying distribution, which is the identity link function. The log function is the one we've been using, and then logit we're about to use. One question you might have, when I think about general linear model, one question I have is like, why are there these particular link functions? It turns out, one question you might have is how do I pick the link function? And the question is essentially, or the answer is essentially, there are canonical link functions for mathematical reasons for each one of the families. So if you think your distribution, your data is coming from a normal distribution, the identity link function is what we call the canonical link. And in practice, we rarely deviate from these. There's mathematical reasons for why they're nice. You can use any link function you like, and there's some choice behind the scenes. But in practice, we just generally don't do it. And you'll see this with the estimation software we use. We don't generally specify the link function. We give it the family of distributions, and then the GLM software will just use the canonical one. So that's about as deep as I feel like I need to go on this. But if you have more questions about that, about like how we pick the link function directly, it's a great question, and you can go deep if you like. But I think we'll leave it there. Any questions here? I see some gears spinning. So this is the example we walked through with GLM last time. This was, we were trying to model the number of children per household. I don't think about children ever. I don't walk around thinking about, this is a silly joke. I walk around thinking about my child every single moment of the day. You think I think about GLM at all moments of the day, and it turns out I just think about Maxine. I don't see maximum likelihood. I don't call it maximum likelihood estimation. I call it Maxine estimation likelihood. It's like, where is she right now? At home, probably taking a nap. Are you saying I'm putting you to sleep?
No. Not at all.
It's
okay. Sorry about that.
Yeah, I'm deeply offended. No, when I do see people nodding off in class, I like to stare at them.
Throwing an eraser at them.
Yeah, exactly. Yeah. I will never throw erasers at you. I'll just throw silly jokes at you. No, you can fall asleep. It's a great place to take a nap. In fact, if you want a nice thing to fall asleep to, you could just turn on my live streams, put an earbud in, and at 11 p.m. and I guarantee that will knock you out. I'm just trying to get my view counts higher. That's all. Go from 2 to 4.
So you can be monetized.
Yeah. Maybe if we hit 5. 5 views per video.
Justin Bieber a few years ago was trying to get people to stream his single when he was asleep. Do you remember that?
No.
He was trying to get people to stream his single when he was asleep so it would go to #1 and it didn't work.
Interesting. Poor guy. No one ever pays attention to him. Okay, this is the end of. It's about as humorous as I'll be all day. So I'm glad we're here for it. Maxine estimation likelihood, or Maxine likelihood estimation. Okay, where were we? This is the thing we were doing last time. We said we never think about children, but let's think about them with data. We're going to try to estimate the average number of children given the data. So this is not just like looking out into the world. We expect there to be differences in the number of children by income. So the more money you have, like especially in this world, it's very expensive. Let me tell you, it's expensive to have a child. So this is definitely a constraint. If you're an economist, you'd expect people to make quantity decisions based on income, which is related to the price. So we could also include like the local cost of childcare in this model, but this is, I think, for our purposes today, good enough. And then it's also, let me tell you, much easier to have a child if you have a partner. Yeah, I could not imagine being a single parent. So one thing we would expect is that people have more children if they're married. Which married, in this model, we're just going to use it as a proxy for having a partner. People can have children without being married. It happens all the time, very common. But this just gives us some additional signal for whether you have a partner to raise your child with. Okay, so this is our model. A couple of things to note here. This is a linear predictor. So inside the exponential, we have just a linear relationship, which we're calling eta. So our link function here is just the log. We're inverting it, so it's lambda is equal to the exponential of x. And this is what we call the canonical link for the Poisson. Okay, so this is the code I wrote up for this. Let me just walk you through what this is doing. This is just initializing, and then we're going to get 1,000 observations. This is x1. So this is I think we walked through this last time, so maybe it's not so useful to do. I think the estimation I ran last time gave us kind of wonky numbers for an MLE kind of reason. The curvature of the likelihood function was very small. And so we actually didn't, you may remember this from the live stream, maybe you didn't see it, or from class. But the estimate that I ran actually didn't get very close to the parameters. So what I'm doing this time is I'm adding some extra curvature, but everything else is exactly the same. So we're just generating some Poisson random data from the lambda. So this is just we have a bunch of observations, x1 and x2, and then I'm just constructing lambda. So this is means, and one thing to notice here, each one of our rows has a separate lambda. This is a separate lambda by observation. So we're not estimating one average, we're estimating an average, like people with higher incomes are going to have a different center of the Poisson distribution. That's part of what we're baking in. And I think you can see this very clearly in the code. We're generating a bunch of observations, x1 and x2, 1,000 times. Each one of those rows has a separate income and separate marriage binary. So the middle of that data, as we're constructing it, will be different for every household. So if we were to plot this just as a histogram, I'm saying Poisson plot, that distribution would be slightly wonky. It may look Poisson, but fundamentally what this is telling us is that there's a Poisson distribution around every point on the domain. So each family is drawing an observation independently from a Poisson distribution with a particular center point. I'm going to show you a picture of this in a second. I think this is one of the easiest places to misunderstand GLM. What we're doing is assuming that every household has a slightly different Poisson distribution. But they're all sort of structured around this, this relationship. So the eta on the inside. Each one has a center. We don't know what that center is. We think the center point for each household follows this beta x. And then we're going to try to estimate that, that specific lambda. Okay, so then here I just built the data frame, and then we can see what it looks like. So something like this. So like I was saying, we have y, which is the number of children. We have the true or false married decision. And then I have the log household income. So this just tells us the important stuff. Okay, so here are the true parameter values. And then we've talked about the estimates. Here it's much more challenging to estimate, to interpret our results because it's a non-linear model. But I will show you a great way of doing it, or at least like two great ways. So these are the true parameters, the truth. So we have negative 0.7 is our intercept. 1 is the coefficient on unmarried. So in reality, we're going to our beta 1 will be 1, and then income will be 0.5. Okay, here's how we did the modeling last time. So we said smf.glm, and then we wrote in the regression equation, gave it the data, and specified the family of distributions. This was the output we ran last time. So here I have this as the intercept. This is right on the estimate for beta 1. And then this is right on the estimate for log household income. Okay, so this is confusing formatting. This shows up a lot nicer on my computer. This is just a note for why the intercept doesn't exactly match the intercept term, the beta 0. So the data generating process, what we're doing by specifying the log, it turns out the intercept is the log of our true parameter is going to be this value, and our estimate was actually 4.77. So even though the number itself isn't quite on, that's exactly what we would expect. That's the short answer here. Let me reformat this later. But that's the short story there. So that our first two betas are right on. Our intercept term isn't right on, but it's exactly what we would expect because of the log. Okay, so that was nice. And then what we can do is just look at the fitted values. So remember, what we're doing is trying to estimate the model that generates the lambda. So each household has a separate expected number of children. And then each household is drawing from that expected number of children, they're drawing a number of children. So it's a random variable that generates the number of children at each one of the households. The middle point of that Poisson distribution is determined by the linear model. Or the inverse of the link function of the linear model. So these are the coefficient, the fitted values. So I have children, and I have household income and fitted values. So that looks like this. And you can see, we have a lot of model error. So in sort of OLS terms, our mistake, so the error term, is just the difference between the number of children and then the fitted values. So you can see that there's a lot of error here, which is to be expected. Every model we fit will have error, but you can see it here. And all I'm doing is just using GLM output dot fitted values to get the values themselves. Okay, so this is all nice. We've gone through and estimated these things. We did almost all of this last class. What I wanted to show you was some extra visualization of what GLM is doing and compare it to OLS. When I think of OLS, I think of scatterplot with a line through it. There's an equivalent way of thinking about GLM. And I think if I didn't have a scatterplot with a line through it, I think my intuition for what OLS was doing would be much weaker. So to develop some extra intuition based on some of the questions I was getting after class and in office hours, I wanted to show you this picture. So this is, I'm going to show you two pictures, one with OLS and then one with GLM, with a Poisson. And this is how I think about GLM. What we're doing with OLS is, we're plotting the data. So we have a bunch of, log household income on the horizontal and then the number of children on the vertical axis. This is obviously simulated data. Look at how many households have 15 children. So this is not real data. Let's just be very clear. In this economy, I guess if you get a nanny, this may be.
That's good. Childcare costs like what, $1 million at that point.
Yes.
No other way.
We have a nanny at the moment. We're about to send Maxine to a daycare. Our nanny has had, I think, 3 children at a time, which sounds like a really challenging job. But let's say you have a super nanny who can handle 15. maybe that would be affordable. Yeah, we love our nanny so much. She's moving away, so it's sad. So anyway, speaking of nannies, number of children on the vertical axis and log household income on the horizontal. And then all we do in OLS is just try to fit the model. We try to minimize the mean squared error, which gives us a line that estimates the expected value at each point on the horizontal axis. So if you're interested in the average at a particular household income, so the average number of children at a given household income, all you have to do is go to the line. And what we assume about the distribution of the error terms, so in the context of OLS, the error term is sort of how far from the model the data is. So the distribution assumption in OLS for our model to give us correct expected values is that it's symmetric. And we also build in this normality assumption. So we have this normal distribution around our model. This doesn't quite look like it's hitting exactly at the peak, but what OLS does fundamentally is hit the peak. So we're maximizing the position on the normal distribution. And then the vertical axis just tells us the middle of the normal distribution, the average of the normal distribution at any position on the horizontal axis. It's linear, just like the data, and we have that expected value. What GLM is doing is something very similar. This shape is coming from the link function. So we don't require the line to be linear, or the function to be linear. We also don't require the distribution to be linear, to be normal. In this case, the number of children is a Poisson process. We don't know the center point of the Poisson, and we don't require the relationship to be linear. What we're trying to do is estimate the middle point of the Poisson distribution at every position on the horizontal axis. And we expect it to be different, just like we expect the middle point of the normal distribution to be different in OLS. So, the reason we do it this way, there are lots of the background machinery is different in GLM, right? It's built on maximum likelihood, but it's fundamentally doing a very similar thing to OLS. Instead of minimizing the mean squared error, we're maximizing the likelihood function, but the core model is very similar. We have a link function that determines the curvature, and then we think about the data being drawn not from a normal distribution around the mean, but from whatever the distributional family is that we're estimating. We call this a family because this is not one distribution, it's a separate distribution at every position on the horizontal axis. But this is the basic idea. So when you think of GLM, think of this. This is like my thumbnail for the day. It's like, subscribe, leave your comments below. Any questions here? I think I'll maybe have one view after today. One person out today is sick. Okay, two people out today. All right, so that was the visualization. You can look more at this in the notebook if you like. And I think that's really all I want to say about this. The next thing is I just want to show you the predictor. I mean, this is very similar to what I showed you in the previous slide. So this is like the number of children. This is, the same kind of model. This isn't OLS. This is, the vertical axis here is the linear predictor. And what you can see is behind the scenes, we're still estimating a linear model. It's just eta, which is our linear predictor, gets funneled into our link function, which gives us the expected number of children. So this is the model, and then around the model, we have a Poisson distribution instead of a normal. So I hope all of you have the mental machinery to do MLE, and you have the sort of mental machinery to do these kind of model building. So what we're doing is swapping out linear models in OLS for like nonlinear models, and we're also swapping out the normality assumption in OLS for other kinds of distributions. We can't copy over all of the machinery into GLM from OLS for how we estimate the model parameters. And so that's why that's part of the reason we require MLE behind the scenes to give us our nice estimation techniques. And then this is happening with like Newton-Raphson.
So, like, in practice with a GLM, you're still limited to things that look like, so the linear predictor, you said, can't be negative, and like based on the link function, like you still, like you couldn't model something that looks like a cubic function where you have like you're limited in the types of curvature you can represent. Is that accurate?
The canonical link functions, I don't think any of them have, like, let's say we wanted like a period.
Yeah.
So like, what if we used cosine as a link function?
Mm-hmm.
None of the canonical link functions do that, as far as I know. But my understanding, and this is like bumping up against the limits of like what I've done and am familiar with, but I don't think GLM doesn't allow you to do that.
Okay.
I think you could use cosine.
Okay.
Actually, I think you can't use cosine because it's not invertible. So the link function must be invertible.
Wait, what? Okay.
Someone could correct me if I'm wrong there.
Why wouldn't cosine be invertible?
I think because there are multiple x's that give you the same y.
Oh, because like that invertible. Yeah.
So there are some limitations there, and most of what I would say beyond this point is speculation.
Okay.
So we're like right up against the limit of what I can answer for you.
Okay. Well, I guess if it requires invertibility, then anything like you could get something that looks like a sigmoid function, but not something that looks like,
That's right.
for example, a cubic function. Is that is that generally?
Yeah, I think that's right.
Okay.
So we're going to deal with the sigmoid in a second.
Okay.
And I think you're right that a cubic, I think some cubics can be invertible, although I'm not entirely sure about that. But yeah, so you can think of like if it like bends back down,
Yeah.
then I think generally we don't deal with those.
Okay.
So yeah, definitely some limitations.
Okay.
The exact like boundary of the limitation is a little bit fuzzy for me.
Okay.
Yeah, excellent question. I love that. That's a wonderful question. So can we do everything with a GLM? The answer is no. The question is how far we can take it. Yeah. Yeah, any other good questions? Or bad questions? Okay, so hopefully this gives some extra deeper intuition for what GLM is doing. I think, if nothing else, what I hope you come away from this class with is the intuition for what these models are doing, when to use them, when they're appropriate, and in some ways like how to implement them. I'm giving you lots of nice code, I think today in this world, having code examples is much, much less valuable than it used to be. But this at least gives you like a groundwork for if you are starting with your own problem, seeing some examples. Often, when I solve new problems, I want to start with someone else's problem first, and then see if I can make it into mine. Okay, so nice. So this is there's a lot of text here. I include these kinds of descriptions. So if you're looking at the notebook, what I'm doing is useful. We've talked about GLM interpretations. We did this last class, so I don't want to spend a lot of time here. But one thing we did was think about whether the impact of a given parameter is important. And so what we did is we thought about these kinds of relationships. So this is like the short story here is the impact of income or marriage depends where we are on the other axis, right? So increasing, like the increase from of a small of going from from marriage to or not marriage to marriage, that depends on what income level the household is at, which makes our interpretation very challenging. Which we're going to resolve this. For some reason, I wrote this in my binary outcome notebook. We'll get there in a second, but we can do. There are certain techniques for making sort of a standard average effect for each one of our parameters. So nice. And this is one of the new pieces I added. I'm just going to run a simple model. We're going to use the children example. I'm going to run OLS. So I'm going to try to predict the number of children using just a linear model. And then I'm also going to use GLM, but with the normal distribution family. And we're going to compare the two estimates. And I'm going to show you that they are identical. That GLM is a superset of OLS, even though the underlying estimation techniques are fundamentally very different. MLE is very different than minimizing mean squared error. So this is OLS. This is just SMF, so stats models formula.ols, and then here's our equation. And then I'm just fitting it. And then I'm doing the GLM Gaussian, not Gaussian. Y'all know Gauss, like one of the most famous mathematicians. So then this is smf.glm, and then this is exactly the same equation. So the eta that I'm defining is going to be identical to the OLS regression equation. And then I'm going to define the link function to be the canonical Gaussian family link function, which is the identity function. So eta is just equal, g is just equal to x. So g of x is equal to x is the link function here. And then all I'm going to do is compare the two models. So the intercept for OLS is -16. The intercept for the Gaussian is also -16. Here you can see I go through each one of the parameters and I take the difference and they're all 0. So I think this is enough to convince you that GLM is a superset of OLS, but we can do lots of other kinds of things. Okay, any questions here? Are you not entertained? Okay, so one extra thing so I added a bunch of things apparently to this notebook. One of them is I wanted to make a mention of the variance in GLM. Our main motivating example here was of children, and that's a a process that generates counts. So this is like a discrete numerical variable, which Poisson is a great way of handling this. With Poisson, lambda controls both the mean and the variance. So what we're doing is when we estimate lambda, we're also estimating the variance of the model, not just the expected value, but also the variance. With Gaussian, there's two parameters. So we have the mean, so mu, and then we also have sigma, which controls the spread. So this is sort of a second parameter we have to estimate. You'll remember what we did with MLE was estimate we estimated Poisson. With maximum likelihood, we also talked about situations where we're not limited just to estimating one parameter at a time, right? I showed you the first order conditions in situations where we also wanted to estimate sigma. So what do we do with the GLM case? How do we also estimate the spread of a distribution, like if we were in the Gaussian situation? So maybe it's it's slightly wrong, I guess, to say that GLM is a superset of OLS, because it doesn't easily give us the same kinds of estimates as OLS does for variance. But this is the GLM Gaussian scale. What this is doing is measuring the spread. And what this line is doing is printing off the OLS residual variance. So the short answer here is the Gaussian GLM gives us the same variability as OLS, but we have to estimate it separately. And the way we do this is GLM is sort of estimating directly the natural parameter. So this is like the middle point of the data. In general, theta, the natural parameter, will be the average. But in some cases, we also have a dispersion parameter. And the short answer here, without going into the weeds, is just that we have to estimate that sort of after we run the GLM. Which is sort of what the GLM model is doing. So it's sort of estimating the first thing, which is our natural parameter, but then in the background, it's also estimating, after the model has been estimated, it will separately estimate the spread parameter, which turns out to be the same, but we do it separately. So this is all really to say that GLMs are what we would call a structured subset of maximum likelihood. Okay, any questions here? And then OLS is sort of a structured subset in a lot of ways of GLM. But I say that with a caveat that the way we're performing these procedures, OLS and GLM, are fundamentally different. Just in the limit, the asymptotics are very similar. All right, very nice. And then last class we walked through model comparison. So this is where we did the likelihood ratio test, which allows us to compare unrestricted to restricted models, which gives us sort of the equivalent of a p-value, which is nice for making probability claims about our null hypothesis, or probability claims about our data given our null hypothesis. The arrow of implication doesn't go the other way. Like we can't make probability claims about our null hypothesis given our data for sort of Bayes rule reasons. Okay, so we don't need to get into this, but last time we did this single constraint test, and then we also did this model selection with AIC, which is this condition here, which you'll remember when I look at this, I think someone is just tacking on like this last piece here is just a like a model parameter penalty. So adding more parameters makes your model worse by some parameter weight. But what this is doing is not that. This is actually derived from theory. So this is not just picking some penalty and imposing it on adding extra model parameters. This is actually a mathematical result, which is why we love it. But this is one way of picking our models is by thinking about the AIC. So that all works nicely. Okay, any questions here? There's also, I think I mentioned this last time, like BIC is very similar to AIC, but just uses sort of a Bayesian framework. We're in the free Quintist framework really all semester. We don't, I'm not going to teach you anything about Bayesian models, so I'm not going to go into the details on this. I think this is where we ended last class. Every once in a while, I think it's worth going back. If you come to my office and we talk about things that I think are worth covering and we haven't covered in class, your questions can feed back into the kinds of things we do. This is, that's like part of what especially grad school is about. So I just want to walk you through a binomial logistic regression. We're going to spend all of the next notebook doing these kinds of things. I'm going to show you why linear models are, in their simplest form, are wrong for these kinds of contexts. And then we'll talk about the link function that makes the GLM appropriate for modeling binary outcomes. And we're going to do lots of different extensions of this. Okay, so sometimes we have data. Or do you want to take a break? It's 10 o'clock. Should we take, this is a little bit early to take our first break. What if we take we're at 9 minutes today, I think? Or was last time 9? Let's go 8. 8 minutes, we'll take a 4-minute break. Just pause here before we get into a new thing. This is an extension of what we've just done. And then maybe we'll have time for a 4-minute break a little bit later too. So we'll double break day. So say hello to your lovely classmates and we'll come back 10:07.
I think you can use your pit account. I'm just walking really fast.
And can you filter by like date?
So you go to economist, and then you go to I just looked up my date. Economist magazine, January 15th, and then you go to all weekly editions, and then wait, maybe look at mine. What week are you? February 7th. Okay, you've got the dangers of the dangerous dollar. I feel like that's better than I guess not all of these are great. Mine's very centered around Iran. Yeah, that's your thing, and then go down. Keep on going. And then there's an ECON section. These are all the countries. I'll go up. It's not. Yeah. I mean, like, that's what I was looking at.
Also, what do you want?
Okay, I mean, yours aren't great either. I don't think it peaked. It'd be interesting. I was thinking about doing the economics of which didn't change, but I don't know.
Do I need a free one? Or is it letting me
I know, it's awesome.
It's like annoying because I pay for the games and my personal one, and like I pay to get the articles, and so I have to like log out and log back in. Depending on what I'm trying to do.
I just log into my parents because they have. I just steal their stuff,
I still steal my parents' Netflix subscription.
and I think that's a good decision. I'm gonna stay on that for as long as possible.
It really kicked me off. Well, it's like, oh, you're not in the.
I know that's
Did
kind
you
of
grab
creepy.
it?
Yeah.
Oh yeah, so you have to actually communicate with your parents
So
about.
you have to tell your parents to log you in.
No, it's nice. My dad always, he's like, oh, so now you're texting me.
I called my mom yesterday to get a password to log into her email, and I forgot she was in Paris, and she was like, "What is going on? Like, why are you calling me?" I felt kind of bad. I woke her up.
Oh no.
And she was like, "Is something wrong?" I was like, "No, I just need the password." She was like, "Emma, it's 2 a.m. Like, why are you calling me?"
That's
Just
so
for
funny.
fun, yeah. They're doing all the fun stuff without me.
Yeah, I know. My parents are going to Costa Rica, and it was like a trip that they had booked as a family during 2020, and we were supposed to go in March of 2020. So I got kicked off because now it's like 50 years later, and
Yeah.
either me or my sister are there, so
Shoot.
they're just going by themselves. We're like, wow.
You know, my parents have been traveling a lot. They're taking advantage of having me and my brother gone.
Same. I feel like my mom's all the time. Like, go make it work. That's kind of chill out.
Yeah, same.
Okay. Well, sorry to interrupt your job applications. It's a very important thing. So let's talk about binary outcome models. This is going to be our first one. We're going to talk about an extension of this. Logistic regression is one of the ways we model binary outcomes, but there's also like probit. So we'll talk about that later. But the basic framework is the GLM can handle binary outcomes very naturally. The one thing we're going to change is that the family of distributions is binomial. So instead of Poisson being counts, we're going to model counts, but just zeros and ones. So it's so it looks very similar, just with a binomial distribution. The canonical link function for the binomial is the log odds ratio. So this is what's the probability of seeing a 1, and then we divide that by the converse, so 1 minus the probability of seeing a 1. So the probability of seeing a 1 divided by the probability of seeing a 0. And then we just take a log of this. This is the canonical link function for the binomial. This is just going to be equal to our predictors. So we can include as many predictors as we like for the binary outcome model. But it's just going to be funneled through this log odds. I mean, I don't know. Do you think this looks nice? Maybe. There's some problems with it, but I think it's reasonably nice. If you, so what you do to simplify and solve for p is you would raise both sides to the e, which just gives you p minus 1 over p on one side, and then you have e to the x beta on the other side. And then when you solve for p, you get this. What this does is it ensures, like, I think this reformulation makes this really clear. But what this does is it ensures that that everything is between 0 and 1. When you run, as I'll show you in a second, when you run a linear probability model, so using OLS to predict probabilities, because it's linear, it can run into negative probabilities or probabilities that are greater than 1. So what this does is ensure that our probabilities are between 0 and 1, which is really nice if we're thinking about reasonability of our models. Okay, any questions? Should we run this? This is really just an extension of our general linear model. So what I'm doing here, I have some random seed. We're going to generate 1,000 observations. I have age as a predictor. So this is just a normal distribution for age. I have log income drawn from this distribution, so it's normal. And then these are the true parameters. Here's the linear predictor. So eta is equal to the intercept term plus the first beta times age plus the second beta times income. And then here I have the probability, which is, this is, I'm not sure why I wrote it this way, but this is this is the same thing as the previous slide, just reformulated. So it's basically just this. And then we're just going to pick our outcome, our binary outcome from a binomial distribution with some probability. So see the steps here? This is linear predictor. Linear predictor goes into the link function, and then we use the predicted probability, which is the mean of the binomial, in the binomial distribution. So 1 with probability prob. So this is the general linear model. All we're doing here is just generating some data, which looks like this. So we have the outcome, which are 0s and 1s. And then we have age and income. And then what we want to do is try to build a model. I wish I had a nice figure here. We'll get into some nice figures in the next notebook for this kind of model. But we can just run a general linear model on this. I'm not sure what's going on with my live stream. Sorry if to the 2 of you watching, which is a running joke, but it's literally almost correct. Sorry if the screen keeps locking. Okay, so it's probably why I only have 2 viewers per video. So this is the outcome of the model, and if we go back to the coefficients, you can compare them. So this is -8, 0.05, and 0.5. So this is -8, 0.05, and 0.5. So we're just spot on. So this is really nice. The comparison between the truth, so this is the intercept, the age, and the log income. This is the estimated, and then we can calculate the standard errors with the BSE. So our model is doing really nicely here. And then let me just plot a little distribution here. So what I've done is I'm holding income constant at a mean of 10.5. So income is being held constant. The reason I'm doing this is just to give us a consistent picture to plot our model against age. So the horizontal axis, so we're basically just slicing our model in the income direction at 10.5 log. And then what I'm doing is plotting on the horizontal axis, I have age. So we're interested in how differences in age for the same income level impact the outcome variable, which I've left generic. The outcome can only take zeros and ones. So the true data is broken up into zeros and ones. So on the vertical axis, there's no raw data in the middle. If you're a 0, I'm giving you the color blue, and then if you're 1, I'm giving you the color yellow. Then what I've done is I've gone through and binned the data and plotted the average for each bin. And I've plotted that in orange. And then the predicted probability, so the outcome of the GLM, is in blue. And what you can see, there's no real threshold. So like there isn't a place where people above a certain age switch from 0 to 1. So there's a lot of messiness here. What the model is doing though is estimating essentially the average probability at each one of these ages. And what you can see is, a linear model would capture a lot of this. If we just drew a line through the middle of the data, it would capture a lot of the shape. There's not a lot of curvature. Like we're not hitting the zeros and ones. But what you can see is that it would. And I'm going to show you an example of a comparison between OLS with a linear model and a binary outcome variable. So this is nice. This is the kind of model that we would wish for. The complication, though, as I've said, is with the interpretability of the outputs. So I'll show you a great way of doing this in a second. If I just say, I'm going to show you later, over and over again, but never get there, would you notice? No answer. Okay. I'll take that as a no. What if I never tell you? So yeah, this is just more to say about this. Interpreting the regression coefficients is challenging, and I'm even committing to this. We'll do more of this in topic 7. So that's maybe about the end. This is just the odds ratio. So if you're interested in odds ratios, part of the reason we like them over some of the alternatives is that they're a little bit easier to interpret. I still find odds ratios not easy to interpret, but maybe if you're into betting, that's easier for you to do. I know like people taking wagers, I don't even know the right terminology, but people do odds ratios somewhat often. Okay, so here are the odds ratios. This is about, so the main point with doing this is just to show you that the logistic regression is a GLM. But we're gonna spend the rest of the class, hopefully just this class, but it may leak into the next class, going into some more detail on binary outcome models. There are a couple of details that I think are worth covering. So here's the summary. the main thing is that we have a linear predictor, but it goes through the link function. And then we use the link function with the linear predictor to give us the model parameter. And that model parameter governs the shape of the family of distributions that we're pre-specifying. And that pre-specification is what allows us to do maximum likelihood. So this is maximum likelihood under the hood, and we're pre-baking the distribution in this way. And then all we're trying to do is just pick the middle point of the data at a whole range of distributions. So each point on the domain has a separate average, which is the entire idea. Okay, any questions? So the next thing we're covering is the binary outcomes. Before we get into that, I have a survey question for you. Originally, I had the order in a slightly different way. Maybe the most natural next step to binary models is talking about ordered or multinomial models. I know some of you, maybe not all of you, are working on censored data or like selected data in your capstone. So what I'm doing is reordering slightly to put that in a higher priority. How many of you are working on that capstone with the censored data? And the rest of you have a separate capstone, which you haven't talked to me about. I won't take it personally. So would censoring, it's like a different set of ideas. We have all of the framework to do it now, but I guess I'm wondering if you have preferences about the order. I'm to like reordering for some of you, but not all of you, I guess. And if you would be interested in moving other ideas earlier for your capstone project, we can chat about that too. But I think that's what we'll do. I'll just put this a little bit earlier. Okay, so maybe I just answered my own question. Thanks for your input, I appreciate it. So let's talk about binary outcomes in a little more detail. Like we just talked about, the logistic regression is a binomial GLM. And then it has the logit link function. What we're going to do here is develop this in some more detail. And I'm going to show you a couple of techniques for communicating sort of average results. In OLS, we have this nice way of communicating average results. If I predict the difference between two groups, I can just tell you the average difference between two groups. We're essentially going to do something a little more complicated, but that will allow us to communicate something similar, the average effect. So we'll come to that in a second. Or will we? And then we'll also talk about what we call bootstrap, which is a way of simulating levels of uncertainty using our sample. Okay, which is a way of skipping the process of computing analytically a standard error. All right, so that's where we're going. We're going to use this data set so that instead of Premier League, which is maybe across the pond, we're going to use NFL field goals. If I were to play in the NFL, I would be a kicker, I think. So what we're going to do is think about whether the kick went in. So this is binary. It's they're set up. The kicker, if you're unfamiliar with American football, most of the game does not involve the kicker, but then every once in a while there's this the big uprights, and then every once in a while the team will bring on the kicker to try to kick the ball through the uprights. This is either a yes or no decision. Sometimes there are fake outs where they actually won't do the kick, even though they look like they will. But we're going to throw out all that data. We're just going to look at the cases where the kicker actually kicked it and it was not blocked. So we're just going to look at whether the kicker was going to making the kick on their own terms. So this is nice, and this is between 2009 and 2019. Since 2019, actually, the success rate for very long field goals has gone way up. So today you can regularly see kickers making above 60, and you're just not going to see that in our data because the averages have gone up. Shout out to Chris Boswell. Okay. So this is just some of the data. I put it on the website, so you can find it at file path, which is just on my website for the class in our data folder. But I got it from this website. So NFL Scrape R was the original data set. But thankfully, we're not using R, and we're using the correct language. Hot take, or is it? Pretty uncontroversial, I would say. That's a hot take in itself. Okay, so this is our data. We have the number of attempts, which is 11,000. And then we have missed, blocked, or made. And what I want to do is just get the number of, so I want to filter for all of the blocked ones. So what I've done here is just filter for blocked field goals. And then we're calling this FG not blocked. This lowers our sample size a little bit. The success rate for these kicks is we're around 85%, which seems about right. And this is just a picture of the field goals. Ooh. So this is the picture. So it looks like this. So the horizontal axis is distance. So we would expect, in general, the further away you are, the harder it is to make the shot. I don't know. Have you seen those? I think Veritasium on YouTube has a video talking about how challenging it is to make very long field goals. I think Mark Rober also has. Y'all know these people? I guess if you know, you know. So Mark Rober, I think, built a kicker, with a machine to try to kick a very long field goal. It's really hard to make beyond 50, especially. So hard that in our data set, we actually don't have a lot of data beyond that. Today, the modern NFL, there are, I think, better balls, so it's easier to make longer field goals. There's a change in the rules for how it can be held, I think, which changes how far you can kick it. And then for some reason, kickers are just getting better. So we actually have people making beyond 60 somewhat frequently. It's just there aren't that many attempts. Like most teams will not allow their kicker to kick beyond 60. It's just there are a few kickers who can do it. Steelers have one of them. Do y'all like anecdotes? My wife teaches at a private school, and Chris Boswell's kid used to go there. So used to be in her classroom, which is very interesting. Okay, so so you can see the kicks go down, the success rate goes down as you move away from the field goal. So what we can do, the first thing we'll do is estimate this with a linear probability model. So we're going to try to predict the outcome of the kick using a model that looks like this. So we're just going to say our outcome variable is just yes or no, so 1 or 0, and then our predictor is going to look like this. I'm going to show you a couple of things. So this is if we try to predict the field goal attempt, the success. So is it good or not? And then this is going to be the predictor. I'm going to show you what this data set actually looks like. So good kick LM, not defined.
I think you just put an extra G in there.
Oh, I'm sorry. That was looking at the data. So this is what the data set looks like. This is the play ID. We have the game ID. So we have lots of information about the specific games and such. But what we're interested in are these two variables. So I'm just going to put in these two variables so we can see what we're using. So this is a measure of how far we are from the goal. So this is the distance measure, and then this is the measure of whether it went in or not. So we're essentially just trying to use distance as a predictor variable. And when I run that, I get this model. So this is as distance goes up, the likelihood of going in goes down by some constant rate. And y'all, I think at this point, feel very familiar with how to interpret these things. As for each additional increase in the yardage, the probability of making the shot goes down by 0.012 roughly. So it's going down by a constant amount, which tells us sort of the average decrease for every foot or every yard of distance from the field goal. But this is not a very accurate model. So let me just run this. When I plot the model against the actual observations, we can see this model is not very predictive, especially at high values. So when most of the data is happening around here, between 15 and 35 yards. So what's happening here is that there aren't that many observations. So the error from these observations is not pulling the model down. But even if there were a lot of observations out here, you would still see that the model would be linear when the underlying data itself is not linear. And that's just the first part of the problem. There are other problems. One of them is that you can see it here. It's making predictions about the success rate for field goal attempts for very small values, giving us a probability that's greater than 1, which is meaningless. One way you could handle this is just to say, let's just censor it at 1. So if the probability is above 1 by our model, we're just going to round that down to 1. But then we're getting into sort of model misspecification. Like, that's not what our model is set up to do. So we're sort of transforming the model after the fact to account for this problem. The other thing that's happening is for very large distances. So, if you're, I don't know, like above 100 yards, what's the chance the field goal goes in? The model is estimating a negative probability. So you run into these sort of domain problems. So we really should be predicting values that are between 0 and 1, but the linear probability model doesn't do that for us. So these are some of the problems with the linear probability model. I will tell you, like, the linear probability model is good on this range, on this domain. For most of the data, this is pretty good. So sometimes, and this is what I did in my dissertation actually, I used a linear probability model because my problem was constrained to a very narrow setting. And we can actually end up in this kind of environment more often when we have more predictor variables. So the more predictor variables you have, the less likely you are to end up sort of falling outside the domain. But for this setting, this is actually not the best model to run. So what we're going to do is compare this model to something that's more appropriate. Okay, so this is just a bit of a description of some of the problem. Here are two different models. We just ran this one. So this is the logit. What we're doing is just giving, we're using the binomial and then using a logistic link function. So it's the log odds, which gives us this. We can also use the probit, which uses the inverse of the normal CDF, which looks terrifying. I actually didn't know this before yesterday, but I don't believe that you can actually write down a closed form for the inverse of the normal CDF. This is one of those cases where even though we can't actually write down the closed form version, it is invertible. So we write down the inverse, and then we use the inverse of the inverse as our as the function. So we can just plug in the function into the normal CDF. So gross but fine. These are both binomial link GLMs. I'm going to show you how they compare to each other. But what we're going to do is fit both and then compare it to the linear probability model. Any questions about this? All right, so let me just run this. This is the GoodKick logit. So this is smf.logit, which is, you could run this with a GLM directly, but I'm running this with smf.logit. And then you just give it the equation. Here's the data, and then we're going to fit it. And then I'm also doing probit. All I'm doing here is just comparing the tables, and we get this. So this is the output of our model. And what you can see is the linear predictor model gives us this number. So this is the intercept. It also gives us just a consistent average. These two, the coefficients for the logit and probit are the parameters that are inside the model. So we don't actually interpret them in the same way that we do with the linear predictor model. LPM is great for interpretations and making claims on particular domains, but it has those problems we talked about. So these are estimates for the parameters, but the models themselves internally are different. So it's sort of challenging to interpret them here. One thing we can do is just plot a figure. So I have all three of the models plotted here. The first is the linear probability model in black. Like last time, the data is in orange. And then I have both the logit and the probit. And we're going to talk about this in a little bit more detail, but there's a reason. I mean, fundamentally, probit and logit are very similar. So the actual models they're estimating are also going to look very similar. And you can see they look a little bit better. And I would say a lot better than the linear probability model. They capture a couple of things. One, they're not going outside the 0, 1 on the vertical axis, so they're not predicting values that are not probabilities. Everything they predict is a probability. Also, they're getting the curvature. So the estimates for these very high distance x values are much closer to reality. And then they're also estimating about as well as the linear probability model these like core samples. Okay, so these are all very nice properties of the logit and probit. Any questions here? It still looks like they're not making good predictions for these these very large values. This is a bit of the conclusion. This is sort of what I just said. So the question that I would have in my head when I see this figure is, why do logit and probit agree so well? And the short answer is that they're very similar functions. Logit assumes logistic errors, and probit assumes normal errors, but really they look very similar. So this is just a picture of their PDFs. So this is the logistic PDF, and this is the normal PDF. And a couple of things to note here. And what I've done here is just match the variance. The logistic PDF has much denser data in the middle. The normal PDF is your classic Gaussian. The logistic has sort of denser tails and has a different shape to it, and isn't the result of the central limit theorem. One of the nice things about the normal is that it's actually just it's like a fact of nature. Like it comes from the math of many independent samples. The logistic is a different monster entirely. But they look very similar, so we'd expect them to give similar outcomes. This is just a description of the two things. Logistic has a slightly heavier tails, and the math is in some ways a little more complicated. The choice of which model to use basically never matters. So this is not something to stress about, which one to use. And they basically give the same predictions. AMEs are the average marginal effects, which we'll talk about in a second. And the way we pick which one is usually just convenience. So sometimes thinking in terms of odd ratios is nice. Sometimes we'll pick them based on theory. So if you expect your errors to be normally distributed, then maybe you want to be sort of theoretically on point and pick the probit. But in practice, these are not going to matter. No one will look at your results and say, why did you pick, like you should have picked the probit instead of the logit. Maybe someone in the weeds will do that, but in general, this is not a big deal. Okay, so this is fine, but I wanted to show you one extra thing. Every model from our previous picture got the prediction wrong for the very long field goals. So we're going to add some extra detail. So what if we add a separate predictor, almost like a binary predictor for whether the field goal is above 40 yards? It seems like something extra is happening out there. One thing you could do is with you could add like a polynomial or interaction term, and you could do this with the linear predictor model. So what I'm going to do here is actually add another variable called yards over 40, which tells us whether the field goal was beyond 40. So I'm going to run this, and then I just want to look at what the data set is actually telling us. Usually, I like to plot exactly the data set, just so I can. Sometimes in general, you don't want to run something that you don't fully understand. So let me just plot out the data set. So this is the data. This is yards over 40, which is mostly 0 because most of the data is not actually plotted over 40 or kicked over 40. So one thing I'm going to do is we can write out field goal not blocked, and then I'm going to create a histogram of this data. And you can see most is clustered around 0. And then let's just see the unique values. So this is unique. So most of our observations are very small. This is just telling us essentially how many yards beyond 40 yards are we kicking from. So that's what this is doing. It's just constructing, it's basically just pulling off 40 if you're above 40. And so this tells us how many extra yards are we kicking. So what this regression is running, this model is running, is so this is the good kick 2 logit. So this is adding a second predictor variable for yards over 40, which is telling us something extra about the data. And then what I'm going to do is just plot this second model. I've run each one of these 3 models on with this new variable. So we're adding another variable, so our fit should go up. And what you can see is all 3 of the models have actually improved pretty dramatically with this new model. We've added another variable, especially for the variables, the data above 40. And all 3 of these models look pretty good. At least in sample. Yeah, way. Yeah, so this is, we're adding this yards over 40 into the linear model. So this is telling us so this turns on when we have a long field goal. So it's 0 everywhere except for the long field goals. So it's saying, we're going to include something extra if it's a long field goal. So we're going to only kink it above 40. So that adds that kink above 40. But we're doing the same, a similar thing for the logit and probit. So you can see the kink showing up in all 3 of these models. And it happens right here. It's much more dramatic for the linear model. Any questions here? So all 3 are improved. and the linear probability model is actually getting much, much closer to the data for the large values. But it runs into a similar problem, almost a worse problem, because we're now hitting zero, like a 0% chance pretty quickly. When we do know that some kickers will make kicks beyond 60. I think even in this time frame, Chris Boswell was making some 60 plus, and Justin Tucker he made a couple of 60 plus. Okay, any questions? So this is pretty interesting. And what I'm going to do here is make some predictions. So I've gone through, let's see, I've made some estimates to construct this figure, and I'm just going to compare some estimates at a range. Actually, I don't print this out because I think this figure gives a better picture of what's happening. You can see the estimates are all generally pretty good. But the linear predictor model is still making non-probability predictions. Where logit and probit are they're a consistent model everywhere on our domain. Okay, and then I think just for fun, we're going to do one more thing, which is add a binary predictor for high pressure kicks. So I don't know. Do you watch football? I do sometimes. There was the Steelers-Ravens game. It was the last game of the season. Anyone a Ravens fan in here? Anyone a Steelers fan? Okay.
When was this?
This was the last game of the regular season. It was this year.
Oh, okay.
It was, it's about as dramatic as it gets. It was Steelers and Ravens were our division rivals, and I forget if we were tied. Do you remember? Was it a?
It was winner.
Yeah. So I don't remember if it was that we were tied in the division or if we were there was I forget exactly how the score was, but whoever won the game went into the playoffs, and the other team, because it was the last game of the season, the other team went home. We were division rivals, so it was we were basically eliminating each other. The game ended up within 3 points. I forget the score there too, but the Ravens set up for a field goal. There was 3 seconds left. If they made the kick, the Ravens would win the game and then win the division and then go into the playoffs, and the Steelers would be eliminated. And they missed it, which in the days afterwards, I remember hearing something like, that situation has never happened before, something, or hasn't happened in 70 years. I was sitting on my couch watching it we have a projector. Maxine was asleep, Molly was asleep. It was 11:30 at night, and I silently screamed as it pulled off to the right. Just the most wild situation I've ever seen in football. All that to say, there may be something different about those kinds of kicks. So what we're about to do is include high pressure kicks in the model. So I'm going to define high pressure as being in the last 30 seconds of a game, and the game must be close. And specifically, you have to be down by less than 3 points, or 3 or fewer points. So you can tie the game with a kick, or you can win the game with a kick, and under 30 seconds. Turns out there are 211 out of these 10,000 kicks that are high pressure kicks. So what we're going to do is just include a binary predictor variable. So we'll call this high pressure. And all we're going to do is use that as a third predictor. So we have our distance measure, we have our above 40 measure, and then we also have this high pressure measure. And this is what it looks like. So we've run our model. This is the logit, which is my personal favorite of the logit and probit. And then these are the model coefficients. You can see this one has become a very large p-value. It was still pretty large when we ran it for the first time, but you'll notice that our p-value is getting larger when we include this high pressure situation. And one thing to note about this is probably a lot of the longer field goals are actually just the high pressure ones. If you're in the last 30 seconds of a game and you're very far from the end zone, one of the best things for you to do is just try a long field goal to win the game. And if you have a good enough kicker, then that's what you do. So that might be explaining part of the misprediction of these long field goals. Okay, so, and it turns out this is negative. So if you're in a high pressure situation, you're actually less likely to make the field goal. But some of this might be coming from the fact that longer field goals or high pressure field goals are on average probably going to be longer. But this is still after we've controlled for the distance from the distance of the field goal, and whether you're over 40. Okay, so that's some of the basics of the model, and the sort of conclusions here. We have two nearly identical models using nearly identical assumptions about the data. Both of them are more realistic than the linear probability model. The linear probability model has those main issues, which one of them is the curvature. So on the main domain of probabilities, it doesn't capture curvature. But then it also makes predictions outside of probabilities. So it makes negative predictions and predictions above 1, which are not ideal. It's not that it's always wrong to do that. I am an example of an appropriate use of a linear predictor model, but using models like logit and probit just will, like, by default give you the curvature and stay within the reasonable bounds. The problem that we're encountering, though, is how do we interpret these coefficients? That's a much more tricky problem outside of the linear probability model. So what we're going to do after we take a 4-minute break is come back and talk about marginal effects. This is the thing I've been kicking down the road. And one last time, I promise you we're going to cover it. Okay, you want to take a 4-minute break? Go do some jumping jacks in the hallway, or apply to jobs or whatever it is. And then we'll come back and hopefully finish this notebook, although I'm not sure we'll get through it all.
Yes.
Okay, so we can do it at the same time. I just like, I just saw something recommended on TikTok. It is. Okay, good. I always see it recommended, but then like the title's like, yeah, it's like giving like Victorian era, like Boston. Okay. Because that's a contradiction because it can't be Victorian. But
Close enough. Old timey.
it's giving those vibes.
My sister was like, cause I'm going with my sister in history, she's like so tight and she was like, you need to plan the entire thing. And so I've been like,
How old is your sister?
dog, she's 2 years younger than me, so she's 21. But I've been like, if you like to book everything she's done, and all she's done is a lookbook, which like, girl,
Style.
so I'm like,
That's really.
this was pretty much an issue.
I love that. I love that. That's what she decided to do.
I know, and she did a good shit. She's like, you have to like everything else. And so
Wait, but like,
she's like paid me for like all this stuff, but I'm like, even my money like
the wardrobe.
and that's where like
I love
she was
that.
like restaurants, she wasn't
Choosing two things that are just completely unnecessary.
yeah. So sometimes I like book the train, book the flights, yeah. Research the hotels and figure out how we're getting to the
When are you going?
So our flight is from May 5th, so I'm going on the 4th. So we graduate the 30th, I have to stay because my boyfriend graduates at a big graduation on Sunday, just like soon.
Oh, that is annoying.
That's the 3rd, so I'm going on the 4th and my flight is the 5th.
Ooh, it's gonna be so much fun though. I'm so jealous.
Also, that's why I've been working so much, because I'm trying to like pick up all the extra
Yeah.
shifts.
Soon though. I know. Do you play bi-weekly or weekly?
Bi-weekly. Which it feels so returning.
Yeah. I get that. Some of my friends get paid monthly, like their songs monthly, and they're like, I like actually can't. Like you're asking me to like go get food or something, but I can't.
And my last paycheck was so little because the way the pay periods are, it was like only the week of sleeping. And I only had one shift, so it was like only my paycheck was for one shift. I was expecting it to be way more, and then I looked at my account and I was like, oh, okay. That's why I can't do fun things.
Who's your pick for the Masters?
Which masters?
Golf.
You all are my picks for master's degrees.
At the golf tournament.
Okay.
Is Tiger Woods playing?
No, not after his
DUI.
previous situation. Yeah.
18.
Yeah.
No, I just played that house. It's like there was questions at trivia yesterday about golf.
We have the NFL draft coming to town, like the end of April. That's the only sports thing on my radar, unfortunately.
Yeah, there's gonna be 500,000 people coming in.
Yeah, what's gonna happen? This is like right around graduation. It's wild.
It's
I
gonna be
don't.
an actual mess.
The weekend before, I was talking to a bunch of Uber drivers and they're like, yeah, I'm like trying to leave town. I'm not even coming into the city.
Oh my goodness.
'Cause they
Yeah.
were like, it'll look like a good ride, but then the traffic that they're gonna have to sit in,
Yeah.
all of that. It's gonna be like
Gross.
I know my friends at Point Park are like completely remote
Wow.
because it's downtown.
Oh right,
so
Point Park
yeah.
University. Yeah. My goodness. Yeah, I don't. My commute is by bike, so I think I'm okay. My wife commutes from Garfield through, like, down the highway past downtown. So I worry for her. It's gonna be crazy. In unrelated news, did you see the New York Times posted an article about Satoshi Nakamoto, the founder of Bitcoin? They think they found him. who has like $70 billion of Bitcoin.
So they were like matching up the language that he used
Yes.
in like a forum before.
Yeah. So it was like the forum before Satoshi started posting about Bitcoin matches Satoshi, and then it's amazing.
They're saying that he like can't use a hyphen correctly, and that was one
Yeah,
of the things that they.
that's one of the tells. Yeah, and then the timing of this guy on the forums matches perfectly when Satoshi took over or started posting, and then when Satoshi stopped, then he picked up again. But they interviewed him, and he's still claiming it's not him. So, but that's exactly what he would say. This is not economics, although I guess some people would think of Bitcoin as economics. You want to talk about how we would. This is like the last thing we're going to do today, I think. Marginal effects. When we're talking about OLS, the average effect of some variable is just the coefficient itself. Like linear model, we can easily make claims. It's just the outcome variable increases by beta for every 1 unit increase in the predictor variable. But this is much less easy to do, much more challenging to do with nonlinear models like this. So what we can do is look at average marginal effects. This is the marginal effect for the logit. So a linear probability model, this is just using the field goals. So the distance in yards, the average effect of increasing the number of yards is constant. So no matter where you are on the field, the linear probability model is predicting that increasing by a yard has the same negative impact on your success rate. So that's in black. So increasing in yards on the horizontal axis by 1 unit will decrease by beta. And that effect is the same everywhere. But for the logit model, this is not the same everywhere. So depending where you are, it's all negative. So increasing the yardage is never increasing your probability. But the effect of increasing your yardage by 1 is not constant. So this makes it much more challenging to communicate the estimates you're making. So one thing we want to do with our model is say, on average, how much is increasing the yard going to impact my probability of success? You could say this in a figure. It took me 3 sentences to do that, and a figure. But it would be nicer if we could communicate this in a simpler way. So that's what we're going to focus on, is how do we make interpretations about our models, because the models themselves are nonlinear, so the ease of communication is much harder. So one thing we could do is look at the marginal effect on the means. So the way we would do this is by looking at the average of the model, average of the data, and then finding the slope at that point. So we say, I'm not going to look at the entire distribution. I'm just going to find the average field goal, which let's say it's right around 35, and then I'm going to find the slope at that point, which here is like roughly negative 0.25. So that's what this math is telling us. It's the slope at the average. So I'm saying how does the probability change when I move in the x direction? So when I increase the distance, but I'm going to evaluate it at the average. So this is one way of communicating. It tells us the slope, but but it has some limitations, right? Like this is definitely better than just reporting a coefficient. If I just report to you the coefficient that I estimated, this tells you basically nothing. So this is an improvement. This first one is for a continuous variable, like the logit. If the variable is binary, then this would be the marginal effect. So basically the same idea, just for a discrete change. So one example of that would be like whether you're married or not for the number of children. So I can estimate that here. So the first thing I do is I just find the mean distance. So we first need to know where we're going to evaluate the marginal effect. So I get the average. So the average distance is roughly 20 yards. That's surprisingly low to me. And then the predicted probability is, the predicted probability of success is right around 90%. These are not the numbers we care about. What we want are the marginal effects at the means. So I'm going to get the marginal effect. So I'm just going to find the slope and then estimate the coefficient there. And this is just some code for how to do this. I'm not sure it's, given the time in the class, I'm not sure this is worth walking through. But this is just essentially two different values, and then I just take the difference. So this gives me the discrete change. But you could estimate this with a derivative if you wish. So this is a way of communicating the marginal effect, which this looks surprisingly similar to the linear model. Maybe it's not that surprising given the picture we saw before. At these averages, the slopes are about the same. Any questions about this? So this is one approach where we just say, I'm going to find the average in the data and then find the slope at that average. But this doesn't really account for, like, there's something missing here, right? Like, I want not necessarily the slope at the average, but I want the average slope. Would be maybe a better way of communicating the result. It's like, what I'm doing here is looking at the average x value and then finding the slope there. But I think maybe a better way of conceptualizing this is I want to find the slope for every observation and then take the average of those slopes. So that's the next approach. Instead of picking one point on the horizontal axis and ignoring all of the others, what I'm going to do is actually look at every observation and then find the slope and then take the average of those. So that's what this is telling us, the average marginal effect. So instead of evaluating at the average person, who may not exist and also is not necessarily representative, we're just going to look at the slope at every data point. So we're just summing over all the observations. And I'm doing that here. So essentially what I'm doing is just the same approach as before. I'm building the model. So these are the predictions. And then I'm evaluating each one in the model and then taking the average, which looks like this. So, and this is pretty similar. Like, there's not a striking difference between the average marginal effect, the AME, or the MEE. MEM. This number is pretty similar to this one, which is, I think, pretty nice. But this one, I think, intuitively sort of works better. It's harder to compute. We're actually computing many, many more things. But I think this gives us a better intuitive average. And we can interpret this pretty clearly. Each yard reduces the probability of success by approximately 1.2%. And then we can do the same thing for any of our estimates. So for this one, we're just estimating the high pressure. So we're looking at the average across the domain, and then just changing whether it's high pressure or not. So if it's high pressure, it's reducing the probability of success by like 7.2%, even after we're controlling for the distance. So even after saying high pressure kicks are on average further away. Okay, and this I think is about as close as we need to be to communicate the marginal effects of our models in nonlinear models. There are other approaches, but this one I think is about as good as we're going to get. Okay, any questions here? This is the code to do it. I don't feel particularly compelled to talk you through each of the steps. Question for you, do you like it when we talk through the code? Is that helpful? Mixed, yes, maybe, yes. I think I saw one no. I don't remember who said no. I take it personally if you say no. So maybe should we just maybe spend a second talking this through? We have like 12 minutes in class, and there's one more thing I want to talk about. So let me just talk you through the different steps. So these are the parameters. So this is the beta. And then what we're going to do is plug the betas into, or we're going to use that later. But I'm just going to take the data. So this is the data set directly. The model output. So this is good kick logit with the high pressure. So this is a model fit. It has a prediction function. So I can enter a bunch of data and then it will make predictions. So what I'm getting here are all of the predicted probabilities. So the probability of success at each one of my observations. And then so I'm taking those probabilities, and this is a list of 1,000 observations. So if you were to take this and put it in a cell and run it, this would just be a list of 1,000 observations. What I'm doing here is getting the logistic PDF. So this is just doing that math. And then for the AME, what I want is the logistic times the continuous variable. So this is the yard line. So I'm getting just the observations themselves, and then I'm multiplying by the yard line. And then for the binary variable, which is for the high pressure, which is are you in a high pressure situation or not, I basically do the same thing. So this is the values for the yard line. This is whether you're over 40, so the distance beyond 40, and then this is just the eta. So we can't use, or I guess I'm using the model specification directly, which I just constructed here to give me the etas. And then I'm plugging that into this function. I forget what special is doing. But yeah, I'm not sure why I wrote it differently in these two cases. But essentially, this is just getting the average. There are 1,000 ways to do this from scratch. These are just 2. And it looks like this. And then all I'm doing here is just printing out the average effects. Okay, any questions here? So the basic idea is we just want to evaluate the points at, evaluate the function at a bunch of different points, which correspond with our data, and then just use that empirical distribution to then measure the distribution, the average of the marginal effects. Okay. And then this is just, I'm going to verify the AME with the logit versus the AME with the probit. And you can see probit and logit, as you would expect from the PDFs that I showed you earlier, the distributions, the distributional assumptions of the two models, these are nearly identical. So if you're thinking about which one to use, I don't have a great answer for you. They're very similar. Sometimes we want a like theoretically we would expect the distribution to be normal. So if we're modeling something that like has central limit theorem characteristics, like averages over many things, then maybe use probit. Logit is better when we're thinking about saying something in log odds. So if you want log odds interpretation, then maybe logit is the way to go. Okay, any questions here? Can I briefly cram into 7 minutes something that's not so core to what we're doing? What we call the latent variable framework. Logit and probit are predictions on 0, 1, but like when we're making a field goal, like it's going to go in or not, but the quality of the kick, like it can go in better than it can go in, and it can like miss by a little bit or it can miss by a lot. There's some underlying measure of like the quality of the kick. And sometimes we care about measuring that kind of thing. This is what we call a latent variable. So we only see the 0, 1, so whether it went in or whether it didn't go in. But there's also the quality of the kick, which in some ways you could measure as like how far from the middle post did the kick go. We do this with lots of things. So this is a useful way of thinking about decision problems in economics, because like we can think of utility directly as a latent variable. We never measure utility, but we do measure the decisions we make based on some underlying latent variable that we call a utility. This is what we call the latent variable framework. There's a threshold that this latent variable gets turned into a binary decision, and sometimes we want to think directly about a latent variable. So we'll say that we have this continuous variable y star, and the way y star is constructed is with this linear model. We don't directly observe y star. What we see is whether y is greater than 1 or not. Sorry, whether it's greater than 0. If it's greater than 0, then it gets turned into a 1. If it's less than 0, then it gets turned into a 0. So this is how we get our binary from a latent variable. We're essentially just splitting it based on its position relative to 0. Above 0, it gets 1. If it's below 0, it gets 0. Which is basically saying it goes in if your quality is positive. So then the probability of a positive outcome looks like this. It's the probability that y is equal to 1, which is the same thing as saying that the error term is greater than this, this is just a reframe of, so you have to use the if y is equal to 1, then y star is greater than 0. So then this is an inequality that says y star is greater than 0. So this thing would need to be greater than 0. And then we just rewrite this thing, we bring it to the negative side. So then that turns into this inequality. This is the same inequality as or the same relationship as this. So this is 1 minus the PDF of the error term. So this is just another way of rewriting this latent variable framework. There's not a lot of depth here. It's just thinking about the binary outcome as some outcome from a latent variable that we don't see. That's continuous. It's this framework that we use for utility sometimes. So this is y star. We can think of this as utility, thinking particularly about utility difference. If you know how to think about utility, you know we can't actually think in terms of numbers. Like numbers are meaningless. What we think of are differences. So, the utility of A being this thing, and if it's greater than 0, we choose A. If we define the utility of B to be 0. So we code A as 1, and then the option we're choosing against, we would code as 0. Okay, and then this is just, we would sort of set this up as the average utility of observables, and then there's some, misspecification term, epsilon, that we would, these choices are going to be in some way kind of random. Like, I know generally what I eat for lunch, but I don't know, it's not the same thing every day. Sometimes I do something unusual, which would show up as the error term. Okay, and that's all because utility is ordinal. Only the comparisons matter. This is the kind of thing we're going to use a little bit later, so I wanted to bring it in when we're starting to think about binary outcomes. But we're going to talk about this a little bit later when we talk about ordered outcomes and multinomial choice, when you have more than 2 options. We're not going to go back to the NFL example today. We'll sort of recap some of this next time and then talk about bootstrapping, which is a different way of getting parameters using essentially a Monte Carlo simulation. So going full circle. All right, so I'll send out, I'm going to be posting the checkpoint tomorrow. Keep that in your minds. I know you have class on Friday mornings, and then you come hang out with me. If you, as always, you can get a no questions asked extension through Monday or Tuesday, and you can avoid coming in and seeing me. This is not a cry for help, I promise. Okay, no one laughed. You got to laugh at that joke to make it work. So if you need an extension, you can't be there, you don't want to be there, you're tired that morning, send me an email and you get the extension. But for almost all of you, I'll see you tomorrow. 1 to 3. I think that's all I have to say. I'll see you tomorrow.